Okay. I had a student today who had this problem on their homework. Estimate the value of the limit if it exists by evaluating the function at values close to where the limit is to be done. If it does not exist, enter does not exist below. So why would someone ask us to evaluate a function at close to where it needs to be done? And what is this terminology? Um, basically, right, if you have a function that is continuous. So it's you're able to evaluate it from negative infinity to infinity. But let's say there's a skip. Let's say it skips a beat, right? So it's like let's say it's a constant sound that's changing in volume, and suddenly it goes out. Doesn't exist. It's not there. Let's say it's imperceptibly small. You wouldn't hear it, but there, if we actually zoomed in on time and slowed time down and looked at this moment, there's a skip here, and everything else is continuous. So the limit still exists at that point, even though there's nothing there, even though there is no f of x. There's still a limit that x is approaching, that f of x is approaching as x approaches this point. So all this problem is saying is if you can't evaluate this with the means that we have, if for some reason the point at zero is clouded, is unknown, is hidden from us, that's okay, because the definition of the limit is not about evaluating that point. That's what's so beautiful about a derivative and a limit, is you're evaluating points very close to that point. And this is why the language of the definition of a derivative and limit are so important. We're bringing points very, very close, but we're not actually evaluating at that point. So that's the whole point of this problem. Okay, because if we evaluate this at zero, what do we get? This goes to 1, 4 to the 0 is 1, and we end up with 0 over 0. That's the typical undefined fraction. So when you see that, we have to investigate further. We don't know. We don't know what's happening. So how do we investigate further? We can often, people make a chart, and you have h on one side, and then you have your function on the other side. And you start bringing values closer to the value that you're trying to evaluate from both sides, right? So if you have this and you have a hole, what you're trying to do is you evaluate on each side. You say, what is it when it's, so in this case, we're going to be evaluating at 0. So what is it at -1? What is it at 1? What is it at -1/2? What is it at 1/2? And we bring it closer and closer, and we see what it's tending towards, right? That's why it's kind of a creative and fluid mathematics. So when h is 2, what do we have? We have 16 minus 1 over 2, 15 halves. So I'm just going to bring h closer to 0. So when we have 1, what do we have? We have 4 to the 1 power minus 1, we have 3. Now, when we have 0, we already figured that out. So really, we're trying to determine what happens between 1 and 0. So then what we should do is evaluate 4 to the h minus 1 over h when h is equal to 1/2, right? When h is equal to 1/2, or when h is equal to 1/4, or typically what ends up happening is h is equal to 1/10, because then you can just make h very, very small, close to 0, by increasing your powers of 10. So what does this graph look like as h approaches like 1/millionth? As h gets really close to 0, and it's going to start tending, perhaps, or if it just keeps jumping, if you keep getting values that aren't tending toward, like what we're seeing here is we're getting lower and lower. So that's a good sign. We're not getting like 2, 1, 2, it's not like hopping up and down. So that means there might be a limit that this thing is going to project towards. So all you have to do is plug into your calculator 4 to the 1/10 minus 1 over 1/10, and then 4 to the 1/100th minus 1 over 100th. And as you do that to 1,000th, you'll end up with this number here, 1.38629. I think that's enough decimals. Whatever your homework program is that is requiring it, might ask for whatever decimal place. So that's how you deal with this problem.